Hi all, this is Claudio from explicit.com with a new live stream. This one is regarding the process of landing on a tarmac runway. Let me give you a small reminder about this process. Let's watch together. What we are going to do is, first we are going to simulate the compression, the touchdown moment of the landing here, which will push exactly as you see here. Will push this fast upwards. Let's see what we can do today in a relaxed manner. Something very easy to understand, quick to do, and hopefully with live results. All right. So a quick reminder about the website explicit.com. Here you can find simulations, tutorials, live support, everything that might benefit your project. So let's firstly see the average pressure in tire has this value 200 psi or 1.4 megapascals, and I downloaded a 3D model from grabcad.com after searching more and many of them. So here my intention now is to start gradually in static and assign the tarmac, let's say. So here, let's create a plane and let's move it downwards. And we're going here to make this driveway. I will, at this moment, I don't want to rotate the wheel because it will complicate things too much. But at least, let's make something like this. I'm thinking about the dimension. All right, so let's pull this downwards. How much? 10 millimeters. By the way, we need to scale this model because it's for toys. It's not very reliable regarding the dimensions, the default dimensions that exist now. Let's kind of ensure a touching here for 4.3. Yeah. So let me move this here, and you know what? Let's move this a little here. All right. So regarding this model, I would like firstly to get your attention. Let's make a section, and we can discuss on this section. Look here. So we can rotate this coordinate system, let's say. Something like this. We can clearly see that it's kind of realistic here, the tire is inside. We have like a bushing or something here in the rim. We do have a shaft, and the shaft is, if it is not now, I will merge it with this part in order to have the sliding of the shaft. So it's clear that the shaft should be fused with this half fork, whatever support is this for the wheel. So this shaft should translate, yes, axially here inside all these supports. Let me come back again for the 3D model. You know, easiest is if we go and maybe say transparent here, and we can understand. We understand now that this part should be fused with this shaft, and this shaft will travel here. If I fuse the shaft with this part, then it will force this spherical joint to work. It will force it. It will move this upward. All right. So we know that this is fixed. Let's say we'll presume that it's fixed to the airplane body. But if this is fixed, then it means that we will have only this travel. Only this travel. This means we can compress only this much, something like this. Yes, so we need to kind of know more. Let's see realistic values. Landing gear dimensions. Landing gear size. Something like this. Once we get some dimensions, we can scale. 85 watt. Please tell me centimeters here. $250, $300. All right, give me a height. So, for example, this shaft, what? Okay. This shaft, oh, he has done some FEA in ANSYS workbench. Perfect. He has only a compression of this shaft, this inner shaft inside. But as coarse as it looks like, and it looks horribly coarse, I think, yeah, there is no translation. Everything is bonded. We can clearly see that it's bonded. And he's not using, he or she is not using Seda etkileşim. Okay. She has done I think, the FEA. Yeah, it's not using, they're ignoring the tire. A thing that I would like, it didn't put the force entirely here. So I would like to keep the tire in the FEA, but let's not digress too much. The height is around, the height of the length of this shaft is 76. So at least diameter is 47. All right. So the length is 76. We'll assume in centimeters here, right? Is someone talking about centimeters or millimeters or something? Of course not millimeters, but the diameter. All right. Come on, you. Why? 36 millimeter landing gear, so it's ruined. You cannot have 56 millimeter landing gear. So, oh my God, I don't want to even question what is here. You know what? Let's go on another. $250. This means if we have a shaft here, is around 1 meter the shaft, all right? Look here, 103, I will assume it's centimeters. So the shaft, even though it's it stays only here, let's say it's 80 centimeters or something. So the length of the shaft is how much? I will click this face and this face. Hopefully we'll get here 120. All right, let's multiply with not 10 times. I will multiply it 7 times. All right. So let's scale everything. How do I scale everything? Pool, scale body, pick an anchor. We don't care, any vertex. Then we drag from the right to the left. And here I said 7. And why not? Multiple of 7. All right, so now we are sure that we have a proper dimension, something like this. All right. So let me firstly fuse these two parts. This is mandatory. Then at this moment I will kind of suppress the pins. We'll use joint loads, and I think this pump, I will delete it. This is important. Also this pin. This pin is kind of mandatory. Let's leave it at this moment. Kind of mandatory. All the pins are mandatory. All right, let's right-click, delete empty components. Right-click, source, internalize all. File, save as. Let's save here version 2. All right, so this I would like to maybe cut it out a little. Yeah, something like this. Let's go here for interference and check for interference. It's only something due to the improper seating here. It should have been something spherical, not cylindrical as it is. Let me remove this. How do I make something spherical here? I can let me copy paste this. Control C, Control V. I paste it, yes. This is the tarmac. You don't see it because it's below, and this is this sphere. Let's hide everything and let's look at this sphere. I will dilate a little this sphere. I will scale it. Look here. Let me scale this sphere a little. But I need a point. can I create a point inside this sphere? It's not inside. Let's just move it somewhere here inside. Something like this. All right. So I have that point. 1.1 should be enough. Let me show you what I'm doing. I will scale this. This is the anchor, and I will scale it 1.15. Okay. What I will do now, I will again show this. Let me make the color of this for easier viewing. Let me make this color like a blue, and this one will be like a pinkish, whatever is this. And I would like to see the, this one. I'm not interested in seeing this here. I'd like to cut out this one. So let's cut this with this, and I will remove everything. I will delete this, and I will delete this. And here will sit this one. You understand? So here, this is how it will be. It's kind of too big. Let's see if we can adjust this. 26.81. It's kind of too big. No merge. 26. You know what? Maybe even this. 23. 25. 24.5. All right. We can always look at the section. Look here. So it looks very nice, only we need to mine this edge in order not to collide. Let's pull this, and let's be very generous. 4.2 millimeters, all right. And here, $25. All right, so we have this. We can change the color to the default. All right, so when we push, what is this? Do I need this? Yes, I need this. Only this part I don't need it. No merge up to this face, because I would like to gain this gap. Let's say this gap, this distance, will dictate the amount of travel for this part. Yes. How much it will travel. All right. So at this moment, just with the eye, we can measure something like this. With control pressed, measure, and we have a distance 87. So the travel. The maximum travel is 87. This travel is from the shaft. Let me write this down. I will write maybe 86, not to touch 87. All right. What about these? Let's see the... okay, yes. look here. Let's see these in section. All right. It goes here on this side and it goes underneath. All right. This is correct. Let's take a small break and see if we have any salutations. Yes, we have a salutation. Singing Fingers, another classic. Hello. Yes, you wrote that if I put them later, you cannot join. So it's earlier. So yes, enjoy and stay tuned. Singing Fingers. All right. So this is kind of too much here. Let me push it here. All right. What do we have protruding and that we don't like? No, everything is nice at this moment. I would want these to be a little thicker. Let's make them, I don't know, 17. Yeah, I would like this to be thicker. Also here. 17 again. 17 again. And do we have something? Yeah, these are the last ones, I think. 17 again. All right. Because look here how thick they are. Here, very thick. Now, if we're going for interference, we shouldn't have. Yeah, there are no interferences. You can read here. No errors found. I hope you can. I hope you can read due to the webcam overlay. All right. So let's not waste too much time. Let's go again in the section view and decide what are we going to do with this. With the emptiness here. I don't care for this hole at this moment, and I would like to fuse these two parts with Control pressed. Look here, if we go in the section view, I fused the fork with the pin, the support of the rim. Can I pull this? Let me pull this. I would like it to be thicker. Yes, we like to have stiff parts. All right, this is. I don't care for this too much, but let it be. So we're going. We have a few methods to take into account this tire. The Nirvana method, the nicest one is this one. ANSYS, hydrostatic fluid dynamics element. Yeah, these are the elements. So this is the Nirvana. Let's see if they have no, they don't have images. Let's go here. This is the element that we should use. But because this element takes into account the proper pressure exertion inside the rim, inside the tire. So something like this, but in reality, this is what we need. There is in the ANSYS help, there is an example with hydrostatic fluid analysis. Yes, And it uses APDL commands. It's very advanced, so it's not for beginners. Today we're going for the beginner approach. I admit that I'm not an expert in APDL, and maybe I can copy paste some commands, but this is not the purpose of this live stream. Look here, how it looks like. Yeah, the one here, 241, is for 2D elements, and 242 is for 3D hydrostatic elements. Feel free to read these articles and examples, and also go for the help, for the example that exists in the help. Here, what are they doing here? Yeah, we can see the difference. Yes, the pressure is applied uniformly, and here is just where near the zone of pressure appliance. But here the pressure is distributed towards the other walls. So yes, this is the nirvana, but we can somehow find a workaround today. Yeah. So I was wondering if I should make also rubber here inside. Let's go with this at this moment, with what we have, and we will isolate the case. Let's see what we can do today. I would like to maybe pull this. How much? Let's get rid of this up to here. I have a simple tire. All right. So let's first apply pressure, and we'll displace this. We'll have only this support, and we'll see how the pressure behaves. Then we will also use the entire assembly that we have at our disposal at this moment. Okay, everything looks nice here, yes. Why do I have this face? Why? Let's go for prepare interference, and we see. No, it's nice. There are no interference founded. At this moment, I'm interested in fusing these parts, this one with this one, or will we use a bonded contact? Yeah, let's fuse them. This one with this one with this one with this one, and that is all. We'll not fuse anything else. Escape. Yes. Then lots of joints. Right click, delete empty components. Right click, source, internalize all. And let's make version 3. Better safe than sorry. All right, so let me open ANSYS workbench. The first FEA will be in static structural regarding, as I told you, this the pressure, the inside pressure. I don't think in static we can use a body to take account of the air. But in explicit, maybe we can materialize that body. You know, if needed, we will. At this moment, let's create this body. So I'm going inside sketch mode. Let's create this body that exists in the cavity of the tire. Because maybe we will use it, we need its stiffness in explicit dynamics. So here, project to sketch. I'll project this edge, we double click this edge, and this edge, all right? Then I will trim this part and this part. Now we have a surface here, which we will rotate with 360 degrees. Click the revolve axis. This is the revolve axis, and we will choose here no merge. Then here, full pull. It will revolve 360 degrees. All right. We escape the command. Then I'm selecting the axis, design, section. So we have the air materialized. In the beginning, we will suppress the air because we will apply instead a pressure. Show all. I'm curious if you see what I'm doing here. Here on this side. Yes. Hopefully you can see what I'm doing. Right-click, show all. Delete any components, source internalize all, and Control S to save. Let's keep this as it is. I will copy version 3 on my hard drive on my work folder. And here let's assign static structural. Let's import the geometry that we have. And yeah, we can close this. Let's name as it is here. All right, so engineering data. Let's apply some materials. What materials do we have in the landing gears? Materials used in landing gear. Is perfect for higher corrosion. Alloy. Alloy it is. We don't contest it. Let's make it, let's make it nonlinear. Nonlinear structure steel. Right. Delete. And for the rubber, let's use a default Moni Rivlin elastomer. For the tarmac, do we have concrete here just for fun? Yeah, we have concrete. Even though it's not tarmac, do we have tarmac? All right, so let's double click. Firstly, this is called stream 15. February 4th, I think, yes. Landing gear extended, whatever, yes. Double click model. How big is our audience? Four people. Oh, welcome. It's kind of a record. On Saturday, I had moments with 0 people, so yeah. Saturday we had around -10 degrees, and now it's warmer outside, and yeah, the audience is bigger, much larger. audience. So let's firstly explore the tire pressure situation. So and I would like to let's compress. Yes. At this moment, I will suppress these parts because, as I said, I will. Let's investigate what we can do with the pressure in tires in the tire. So I will pull this down. F9 to hide the body, and here is the air. Let's let me show you. This is the air which is materialized. This is the tarmac which is. This is the main shaft. How do I call it? Shaft or fork or support? Let's call it fork. Why not? Right-click show all. This is the actual tire, and this is the rim. All right. Fork tire rim. Structure still nonlinear. Tarmac is concrete. Let's call it concrete, not to despair people. Air is air, but we don't use air at this moment. We can use the air in explicit dynamics. All right, let's see what contacts do we have. Let's use default. By default, everything will be bonded, of course. Tied to concrete. Let's leave it bonded at this moment. Tire to rim, and it's bonded here. Yes, and fork to rim. Yes, let's leave it like this. Yes, even though we should use a Revolve joint here. Yeah, now we're investigating the air pressure. Control S to save, right click, generate mesh. What's the deal with, there are two parts, come on. Why are you thinking so much? Maybe I was too generous here. For the quality, I will give smoothing. Maybe change the smoothing. What's the deal? Come on. What are you doing? Stop it. Let's use here low for smoothing, and maybe it will go faster. Also, do I use a virtual topology? General virtual cells. Yeah, we have some rounds here. Yeah. Show all bodies. All right, generate mesh. Why so much? Come on. Too much thinking. So this is how it's going to be. The tire gives some problems. All right. So what do we do when we have problems? We investigate and solve them. Section planes here. Let's make a section plane here. What is the problem is here? There is a, yeah, there is something fishy here. Here there are kind of overlapping faces. Look here at this face. Something is overlapping. I think we have like a surface, like a face here. And it's coming from what? You know, let's shave this. Because I don't like this this face. I don't like it at all. Double click. Any message? No. I'm searching live for materials, for pressure, for loads, in order for everyone to see that it's very easy to find this data, and you don't need to be an expert in that field. Our purpose is FEA at this moment. It's not the purpose is not aeronautics. No, that's found. Yeah. All right. So let's shave this. Let's change the color. Okay, this is more pleasant for the eye. Sketch mode. Let's shade it because it's something. Look here, it's something fishy here. I think we need to also remake the air because of that fishy thing here. All right. Come on, I told you. All right, so I promised that I will kind of shave this, but how should I do it? Let's firstly project this edge and this edge. Also this one and this one. I would like to use only this portion. All right, let's offset. I will offset, but how much? How much should I shave? 0.1 maybe. And here again 0.1. 0.1. All right. So I will shave with this. A reminder to come to also do something like this, maybe. Yes. Can I mirror this? Just asking. Can I mirror this? Let's see. We will see. I'm interested in, should I shave everything? Yes, let's shave everything. Let me close this. like this. All right. And now we are going for trim. Let's mirror if it is possible. Design mirror. I will select this axis and mirror this. Not all constraints. I don't care about constraints. All right. Let's see if I don't have a surface. They are curves. When there are curves, then the sketch is not fully defined. Let's say. We have an extend from here. Can I extend it here? All right. And it should work. It should be nice. Here it's blue. I don't like this blue. But I have to live with this. All right. Let's mirror again. Not all constraints. At this moment, I don't have a tool that says fully constrained sketch. Yeah. In dedicated software, there are tools for fully constrained sketch, but I don't know to exist. Here, curves again. Can I somehow... No, the other one. Come on. Cooperate, please. Let's extend this to here. And there is a problem with this contour. I think it's regarding this approximation. Can I delete this? Maybe shave everything? Yeah. Let's delete this. And I will (180°). All right. Let's also prolong this somehow like here. And let's mirror this. Design, mirror, this is the axis and this is the curve. Two curves, this one and this one. All right. Now let's trim what we have extra. This is extra, this is extra, and let's shave with this thing which is overextended. Yes, it's extended, for example, here on the left, and also it's extended here on the right. Let's kind of shave with the cavity where the air is supposed to be. No, we don't want. All right. We should have a surface, but we don't have a surface. Should we take it from 0? All right, let's take it from 0. How much? Maybe I was a little too cheap. 0.5. All right. Now let's unite these. Now it's upwards. Let's unite these with the line, this one and this one. Yes. And here, let's extend this. I will extend this here to here, and this here to here. All right. Come on, now it's the cleanest. We have a surface, finally. Let's cut, pull, axially, of course, about this axis. Let's cut, and here, full. All right. I hope this will not give us problems. Can I delete this just for fun? Yes, I can. Let's delete. If I delete it, I will have let's delete it, and I will make a cutout with the rim, you know? Yeah, let me delete all these, and I will cut with the rim. Where is the rim? This is the rim, maybe. Yes. Let me cut. Design, combine. This will be the cut part, and this will be the cutter. Unable to intersect bodies. Prepare interference. Can I? No. So let's refrain from cutting these faces. Yeah, I hit undo. Right-click, delete empty components. Right-click, source, internalize all. File, save as. Let me save this as version 4. All right. Let's also show this, and let's see in section what do we have, because I think we have another topology. For example, you see here, the rim is cutting into the tire here. Here, this face is correct. Let's, for example, find that this diameter is 1554, and this diameter is 1.554. I bet there is an approximation. They are not exactly the same diameter, I bet. They are not exactly the same diameter. Let's do something like this. Let's make these two 156. And the rim, let's make it also 156. Here, 156. And now we're clear. We're perfectly convinced that everything is touching. Yes. How about the air? Should I make the air? Let's make the air again. Double click, click, double click, click, and we're trimming this portion and this portion, and voila, we have the inside air. I will click this face, design, pull this face with about this axis. I will click no merge, and here the full pull. All right. For you to be convinced, you see, rim, air, and the tire. No, this is the air. Come on. Air. All right. I don't need this point. Maybe I need the plane. Right-click, source internalize all. Right-click, delete empty components. Control S to save. We're going. We're leaving this. Why? Because if we leave space claim open, it will import faster. Right-click, update geometry from source. And hopefully we'll get rid of this face that was problematic in the past. This one, yes? Hopefully. Come on. What are you doing here? I don't know what is going here. You know. Ah, it's still importing. All right. I guess. Why don't you import? Why? Let's write here v4. In order to be 100% sure, we'll replace geometry with this one. Double click. And now we're 100% sure that we're going to receive and import the proper geometry. Anything happening here? No. So, 0% audience. All right. Let's hope in the future I will make these presentations more attractive. This is the fork. This is the tire. The tire should be made of elastomer. The rim structural steel, and the concrete is concrete. And then the gear, what is this? This is the air, which we will suppress at this moment. We don't care about it. All right. Let's ensure now that we have a proper mesh. Yes, this is a very good starting mesh. You know what? Because we like it so much, let's duplicate this. I got rid of that touching face. Yes, it was some work. Maybe it was a modeling error, but we solved it. So now I'm duplicating this scenario and I'm working on a copy. Let's watch again this. Okay. Yes. I said that. Let's move a little. Something like this. I said that at this moment we'll leave it bonded. Just rubber to concrete coefficient of friction. It should be very high. Yeah, oh my God, 0.6 to 1. Static kinetics. All right. Here, right-click, rename based on definition. Fork to rim. Here we should have, we will have revolute joint a little more in the future. In the next, I don't know, half an hour maybe. Tire to concrete, tire to rim, yes, and everything like this. Let's do, as I said, something like here. Let's apply the pressure. Yes. Let's also suppress this at this moment. Let's firstly apply the pressure and see how it behaves. 1.4 megapascals, which is 200 psi, pounds per square inch. I can also suppress this. Let's fix the. Let's fix this. Let's see what the pressure gives. 1 point, yes. Large deflection on, solver type direct. What does it need more? Come on, we should have enough. Elastomer contains invalid property data. Why? Let's see. It doesn't have something linear. For example, this one and this one. 1000 kilometers per. And here, usual for tire rubber, young modulus for tire rubber. Let's see how much. 10, 11 megapascals. Yeah, why not? Then it is 0. All right, closer to 0.5. Yeah. Save, and let's see live what we can obtain. Switched automatically. All right, save. Solve. I left the mesh to coarse. Once I stopped, okay, it stopped. Let's make the mesh finer. 25. So let's make this this as maybe 35. The general, and this only the tire, the meshing of the tire. Let's make it 25. Yes, it's just a check, all right, on how the pressure behaves. Solve. So it solves very quickly. Oh, it looks very nice. Oh, very nice. Yes. Perfect. What is the problem is that I think this edge will cut here. There is this edge which will cut here. Okay. You know what? Maybe let's go with the smaller value for the pressure. Yes. It's so nice. I'm thinking about assigning that this radius here, because we have a sharp edge from the rim. Look here, the rim is cutting here. Let's look a little at the contact tire to rim. Yeah, it's good. It's good. Only, yeah, it's cutting here. Should I assign that radius or not? Let's make that radius. Otherwise, it will kick us in the behind. If we leave it like that, we'll create more problems. If we leave it like that. But yeah, nevertheless, it's promising. On the first run, the applied pressure, yeah, is nice. So as I said here, let's go in section view, design section, and I will just direct this point. Yes. So this one and this one. 2.5, all right. So we'll have a smooth surface for this rubber to dilate. Will not have a live edge there. Yes. Maybe I should have rounded this, but because should I round it or not? Yes, let's round it. For example, this and this. The problem is that I don't know what I'm selecting. Okay, this and this with Control pressed. We'll make it again 2.5. This and this. Pull. Pull. Why don't you pull? You don't want to pull? No? I don't know how much. 10. 10 here. All right. 10. Now let's hide this and show the air. This, all right, and show the air. And now I will pull here, yes. This is 10. All right, and now show all, and you can see that it looks nice. All right. Right click in delete empty components, source internalize all. Show yes. Let me see everything. Something like this. Control S to save. All right. Yes. I will repeat the FEA. I will revise the contacts again. What is this interstage? This is what additive material bond. This is interesting. You know, I should look on this. So only one contact at this moment. Yes, why not? And it's a proper contact. All right. Yes, I would like here to select more faces. Right selection, adjacent. It spread a little. Yes, it spread a little. Because maybe part of this face will touch the blue. Come on. Yeah, maybe part of this face will touch here. This is why I extend it. Of course, it shouldn't be bonded, but let's not care too much at this moment. 200, I think it's kind of too much for what we have. Let's make it 1 megapascal. And here the sizing, let's make it 30. In order to find these faces very well, let's assign mesh sizing on this face. And the mesh sizing will be 20 maybe. Okay, 20. Or maybe 15. Let's make it 15. I will hide this body and also assign 15 on these faces. And we're making sure that we will have proper touching nodes on each side. Look here. Sure. So. Could have been better. Let's not care too much at this moment because I'm just verifying the pressure. Once I have the pressure stabilized, I can come up with, or maybe no, come down with the landing gear towards the tarmac. I can also do the other way around to push the tarmac on the landing gear. But let's do it as it is in reality, yes? The landing gear presses on the floor. Clear generator, yes. Solve. Come on. Do we have anything from our large audience of 3 people? Hello, welcome. So now we're verifying the effect of the pressure, the inner pressure on the tire. Then after we have a proper behavior of the pressure, we can clearly press with the rest of the landing gear, we can press on the tarmac, yes? Just in 1-2 minutes, you will see more parts. We will begin to unsuppress them and apply joints as it should be. The FEA runs very quickly because I have a pretty coarse mesh. Usually when we have hyperelastic materials, as it is the case here, we should, yes, elastomer monireflin, we should use finer mesh, but now we're proving that, and we're testing the behavior of the pressure inside this tire. So in a few minutes, we will have a little finer mesh, not too fine, because you can see that dissolving it takes a few minutes only for 2 parts. Just imagine when we will have these, I don't know, maybe 15 parts, dissolving will take much more. So I have applied, it's only one step. This is why there are some convergence issues. I should be more generous here, not to leave it program controlled, but applying some values for manual time stepping, let's say. Come on. Yes, it works. Let's see at this moment if we have some only to this, if we have some landing gear simulations in ANSYS. Landing gear. Do we have landing gear? I know there are some. This is not ANSYS. Oh, there is something here. Nose landing gear. I'm curious if they keep the. This is very nice. I'm curious if they keep the tire. Oh, what is this? It's explicit, yes. How much does it take? It's a pretty small time step. And I don't want to waste too much time here. Look here at the time increment. It's very small, so, and I sincerely don't like it. I think it's due to the rubber. Let's see. So, yes. I like it here, how it looks like. And I think it's still too much for what we have here. So let's keep this as something that is promising. I will write here promising. And then we'll begin to unsuppress the other parts. I will watch my smartphone for a second. Okay. So I'm duplicating because we're gradually we're going to have nice behaviors. So as I said, I will. Ooh, I forgot to apply it also on these rounds. Here on selection limits, apply, and it's also applied on these rounds. Instead of 1, let's make 0.777. All right. Right-click unsuppress all bodies. Because I'm satisfied with the pressure, I will suppress the air. And Let's see what joints. We should put some subjoints. Let's make this contact right-click, create automatic connections. Right-click, rename based on definition. And I would like for tire to concrete to be as expected, to be frictional 0.6, yes? All right. Other contacts. I don't want sincerely, I don't want to have other contacts except tire to rim. Tire to rim. All right. The other contacts, let me suppress because we are going to use a heavy load of joints. Suppress. So I have this with this and this with this. That's all. Then now we're going for the joints. Here, connection group, or how do I? It will create automatically. Let me hide these. I will remove this section. So let's create this joint. This one and this one. Connection, body, revolute. Does it work automatically? No. Why should it work? Huh? Oh, it worked. Yeah. I feel sure. I would feel better if I changed that face to this face. Just to be sure of what I'm doing. All right, another. This face with these two faces, all right? We can argue that maybe we should select these faces. Let's do it just logical to be very clear for everyone. Body revolute, this face with these two faces. Body revolute, again, this face with these two faces. All right. So the other thing, I have a translational joint between these two parts, body translational. Then a translational joint between this shaft and this part. Yeah, this part. Let's hide other parts. Yes. So between these two parts, translational. And now let's hide this between these two parts, all right? These two will, come on. Yes, you can verify here on this window. These two will translate axially, all right? One to each other. It might be that this will touch this face. If this will touch this face, let's assign a contact, you know? What? Let's look a little in section to see what's happening here. Yes. So this shaft is kind of bonded here. So let's see how this part is called. This part, the green one. Let's see how it's called. Selection mode, single select. Right click, show in body tree. Come on. Show it in the body. Show it in the body. Go to corresponding bodies in tree. It's called steering top head. So steering top head with the fork. I will look here on the contacts and remember about steering top head and the fork. Yeah, this is the contact between the two. Let me unsuppress this because this should be bonded here. Yes, maybe it is threaded, is screwed in. Maybe the shaft is screwed in. Maybe we don't know at this moment. So let's have that contact there. I was here. All right. We can apply this revolute joint here. Click body revolute, and it will touch with these two faces, this one and this one. This is the revolute. And now the spherical joint here. Click this face, body spherical. With the easiest way is to hide it. F9, click, and here. If I show all bodies, you can see that this one is touching, is joining here this spherical, and only this spherical face, not this cylindrical face. All right. So more parts, more. What have we here? Or did we already assign? We assigned here. Let's go on this branch. Body. Revolute again, as we did before. This surface, then these two faces. Again, body revolute, this surface, and these two faces. Do we have something more here? Here there is something. Yeah, let's have a contact here. So with Control pressed, right click, go to contacts common to selected body. So we should have this highlighted. Yes, this is a very good option to find these contacts. Unsuppress. We have a bonded contact here. I'm thinking if I should let it rotate inside. I should let it rotate. This means then I should maybe... Yeah, let's suppress this contact. And let's instead assign a revolute joint. Yes. Between this. Yes, it was a pin in the past, yes. let's have a revolution between that and this. And they will be able to rotate, all right. Now I have here a small joint. What do we have? Here is this one. Show all bodies. I don't care about this one at this moment. And about this one, I don't care. I care about this thing. All right, so do we have a pin here? We have a pin. Let's suppress it. Suppress this pin. And instead assign a body-body revolve joint. So this one, as we did in the past, with these two ones. All right. Right-click show all bodies. And this with that one, body-body revolute. Control F. And here we can choose from here, from this stack, you know. For example, here, this one. And here I will select the third one. And you can see it here in the window. You see, this one is joined with this face. So it's good. Remember about this stacking. Options. Didn't I join? I didn't join this. You know what? Let's go for the contact common. Contacts common to selected bodies, and I will unsuppress these contacts. Why do I have two contacts? Unsuppress. Because it's contacted here and here. All right, that is all. I would also like to have why do I care about this contact? I define the joint there. This one. I'm wondering if this should rotate. It looks like yes, it should rotate. Yeah, so again, let's suppress it. False alarm. Let's create the revolute joint here and here. Also the same here. This is one part. Let's look at the contacts for this part. Contacts for selected bodies. I have this one, and this one. All right, let's see this contact. Why is this bonded? I don't think it should be bonded. Suppress. All right, what contact do I have here? This one, territory. All right. I think we will see more contacts and joints. We will see while the FEA develops. All right. All these, let's make them structure still nonlinear. Let's mesh. Let's make all these parts tetrahedron. Control A, apply, tetrahedron, generate mesh. And instead of 30, maybe let's go for 25. I think I was too generous with the tire. Let's make it also 25. Yes. Yes, let's... Do we have like a gap? No. So now let's come with this downwards, all right? So we'll fix the tarmac, Control A for surface. I have the pressure inside. Only at this moment, because firstly we have the pressure applied, it will kind of collide with the floor, with the tarmac. Let's see. Let's keep it like this. And I will press this, yes, I will displace it downwards with maybe something like 70 millimeters. Yeah, 50 millimeters, I wanted to say 50 millimeters. So displacement, this thing, yes, 50 millimeters. Downwards means minus 50 millimeters on the y-axis. Perfect. Let's have it like this. And by the way, 50 millimeters is below, as I wrote, below 87, 86 millimeters. You remember the amount of travel that here maybe we will have such a travel, maybe. We will see if there will be. No, it will not be such a travel because of this joint. So it will rotate. This thing would rotate about this axis. Yes, let's see how it behaves, maybe. How many nodes do we have? Oh, 90,000. All right. I think I should have used some rigid parts. Let's, for fun, let's make here 2 steps. Instead of program controlled, let's, I like to have time 1, carryover time step 1. We will begin with 0.1, 0.01, even though we have the rubber. Let's make it like this. I predict that the rubber will impose a very small time increment and time step. All right, and here let's make it gradually, minus 25 and minus 50. Yes, it will compress. Should I make it maybe to rotate a little? Should I make it to rotate a little? Why not? Why not? Let's apply what's on z-axis something. Let's apply what? How much should we apply? 100, 200. Ooh, 100. Ah, 0, 25, and 50. 25 and 50. Minus 20, minus 40, 20, 40. All right. Control S, and fingers crossed. I'm curious what contacts have I forgotten, or maybe joints. Let's see. Anything from the audience? Any question or something? No. Okay. So I think I bit too much. I took a bigger bite than I could swallow regarding the first time that I've seen this model. Let's see if it will converge or not. So we're displacing downwards. We have these joints. All right, I have this joint. Yes. And this is the bonded, all right. So normally, so I'm pushing here, here. Here. We have the spherical joint. All right. Yes. Here I go to joints common to selected bodies. I have this one, all right. I can see it here, all right. Come on, let's see if I overcomplicated. In principle, it begins well. But it's not coming from top down. Huh? Ah. Yeah, this displacement is due to the pressure. It's not here due to the top-down displacement here. So this deformation is due to this pressure. All right, let's duplicate. I will suppress some parts and test to see where the problem is. There is no legend, and we know why, because the time is very short and it gets out. No body contact, come on. This is a shock. Why do you publish something like this? Why? And here we can see that there is not a proper contact. I would go so far as to say that the wheels are rigid, because in principle this, according to me, yeah, rigid one. Yeah, there is no flexibility on the tires. Nevertheless, it looks nice. What I want to do is, I'm not interested in these at this moment. Even more, I would like to suppress this. I'd like to fix this. Let's see if it, what is doing here, if it travels. Yeah. So I fixed here and I am displacing here. Let's solve. Then we can see where the problem is, because usually the nonlinear contacts give problems. Maybe also having the hyperelastic material, it gives problems. Usually such a scenario is to be debated and researched and tested for days and weeks, and doing it in 1, 2, 3 hours live, it's a big stretch. I think it will work. So here is only rigid. Hyperelastic material. Oh, what? Let's see. Yeah, this is Nirvana. Until now, on what I've seen in ANSYS, in my eyes, this is Nirvana. Very nice. Very nicely done. 13 years ago, very nicely done. It's already liked. Let's go here, and yes, it's going nice. Yes. Come on. I need to see here flexion. I mean, yeah, this angle should lower. Yes. So it pushes here. And also here. So there are 2 points where it's displaced. It's displacing here and here. And these two should slide on the shaft. Yeah, so it's clear for me now that the wheel is posing problems. It complicates the simulation. Ah, what? What is this? Go to contacts for selected bodies and go to joints for selected bodies. Only this one. Ah, it's flying away. I should have have the revolute joint here, and maybe a contact, frictional contact here. So let's animate. Gradually we're seeing where the problem is. Yeah. And let's assign contacts between these parts. 1, 2, 3. Let's assign contacts in order for them to touch each other. So where is the geometry? This is the geometry. All right, so let's have a revolute joint here because I know we don't have it. And let's have a contact. I will do it by hand. I don't want to. All right, contact frictional. Yeah. No, 0.15. Steel with steel. All right, and these contacts. This contact should be frictional 0. Control F, frictional 0.15. This contact, this face, should have, again, frictional contact with this face, 0.15. And that's all. All right, so maybe I should go with a little more. Minus 30, minus 60. What? 30 and 60. Oh, I have a mistake in there. All right. Wanting to have also rolling of the tire, I applied this orientation, and I think it's kind of ruining this specific scenario. It would be, I think, easier to come straight downwards and not inclined. All right, let's see. Do you have any question? No question. Aircraft nose landing gear. What? This is a, I thought it's a tire and the rim, and no. No separation. Friction, yes. No separation between who and who. What contact? very fast, lightning fast, in order not to understand anything. No separation between the and the what? No separation between the tire and the tarmac? What? What are you doing here, man? Or woman? Very fast, yes, very fast. So anyway, we have nothing to see. There is a joint there, all right. Why don't I hear the CPU running? Come on, dude. What have you done here? Ah, they are rotating something. Come on, what is... No, it's... What? Very weird, very weird. No, the wheels don't rotate. You can see that the screws, they remain in the same position. Maybe everything is out of steel. No, it's... No way. No way. No separation. The bodies are not in contact and they're applying no separation when they are 1 meter apart. I don't know if it's laughable or sad. Maybe sad. Why isn't this working? The dependent term of internal could not be it is like displacement when it will be into concentration. Oh. Maybe I ruined something, I over-constrained something. Maybe. All right, so we have frictional there, we have frictional here and frictional here. All right, it looks nice. Remove it. Let's revert to what we have. Maybe if I change this to bonded and these two to bonded, maybe they will help the solving. But this needs to separate. These two can be joined together, I think, but these need to be separated. Let's, if not frictional, let's suppress this. This stays. This is clear. This is the maximum. Yes, we don't need this contact because this only goes down. We don't need this contact. And this, yeah, let's keep it. All right. Yeah, something is not right. Multiple constraints have been applied on degree of freedom 2 of contact node. All right, let's copy this. Rigid constraint surface identified by real constant set 57 and contact element 57. The degrees of freedom of the rigid surface are driven by the pilot node, which connects to other element. Internal MPC will be built. And this is not necessarily an error. Right-click, select mesh by ID, paste, create name selection. Let's see where this is this node. What? It pertains to a suppressed part. I don't understand. Element. Okay, let's see the element. Right-click, select mesh by ID, elements, paste, create name selection. Why are they suppressed? So we ignore them, no problem. Let's go here with this one, warning. Or use relaxation option to overcome the over constraint. If I would know which joint is what we're talking about. This is element or what? Node. Finally, we have it. And there is a problem with this joint. Should we care at this moment? Let's make a bonded contact because, yeah, because it's overcomplicating here, this joint. Suppress, and here instead of the frictional, let's make it bonded. All right. Anything from the audience? No. Tutorial, ANSYS simulation. What do we have here? It looks, it's a very nice geometry. Fixed. What? You are fixing? What are you, why are you fixing? Why? Why? What? Why do you fix? Why? A plane is not fixed. A plane is flying. This is the purpose of the plane. To fly. Why do you fix? So much time, so much effort to fix. You could have selected everything. Select from the right to the left. Select and apply a fixed support. A fixed support. Why do you fix? Why so much time? Look here, 7 minutes. Oh, we have Revolute. Finally, we have Revolute. So we have some Revolute joints. Revolute. Revolute? You apply Revolute fixed? Fixed rims? What? Come on, why? Why are you doing this? Why? Fixed Anush, Mr. Anush is fixed the tire to the rim. Come on, why? Why are you doing this? Joint load. X-axis. X-axis. This might work. 250 everyone, but on the so it's going like this. It's going towards the Y. It should be going towards the Y. The assembly, each sub-assembly, it should be going towards the Y. It meshed and already solution. Let's see. Animate. Come on, we're curious. Why are you changing this? Why? Show the results. Animate. So it worked. Yes, it worked. So in the beginning I thought maybe there was a landing, but no, it's a retraction. The opposite of the deployment. So my apologies, Mr. Anush, you have done very well this this deployment, this opposite of deployment, retraction. This is kinematic. So Mr. Anush knows what he's doing. Again, apologies, Mr. Anush Kaushal. We have something to learn from this person. Yeah. Respect. My respect. Finally, something with flexibility, I think. Oh. What? What? It works? What? Yes, it works. This will touch here if I push it more. Yeah, let's unsuppress the tire and the rim and the tarmac gradually, because let's see. So this is very nice. Finally, something that works. It's very promising. The gears are still rigid. They look rigid. Only this portion, this sleeve, is flexible. Yeah, nice work, nevertheless. Anything from the audience? No. Where were we? Here. Let's unsuppress everything except the air. We don't care about the air. What is this? This is the PM. And we suppress the PM. We don't care about the PM. Yes. There will be a pressure. I have the intention of lowering this a little. But let's run with what we have. We might be forced, if it does not work, maybe I will bond this, because having this as a frictional, and here with the hyperelastic, it will create many more problems. Problems which cannot be, usually should not be solved in 1 or 2 hours. They should be solved in a few days. What is this? What? Why is it not working anymore? Yeah, weird things. But with persistence and patience, we solve everything. So I was hoping that this will impose a rotation here. What I didn't do, and maybe I should have done, maybe I should prescribe like a planar joint here in order to ensure a straightforwardness and to ensure that this will not rotate. Even though we have these links here. I bonded this. Because I bonded this to this is forced to be straightforward, to be in plane by these other rods. D is being bonded. Yes, we have straightforwardness, let's say. And this forces also the fork or the shaft, they force to be only to move, to land only about in the YZ plane here. All right, to move only on this plane. I feel something promising. Yes. We like green vertical lines. Okay, let's let it cook for a while. Landing gear struts. This is something static. This is very nice. We should look at this. Look at this. It's, oh my God. On a molecular level, it's so much. I think they used hundreds of millions of cells for this CFD. It looks so nice. It's mesmerizing. This is made with add-ons. Titanium? It's in SolidWorks. What is this? My God, the resolution, my God. I hear something nice. Oh, why does it look nice? Do we have decent results? Or maybe I forgot something. Yeah, I forgot these ones. I forgot these ones. Let's look a little at what we have here. I was surprised that it was going. It was going too nice. Yeah, let's pause it because I don't have the proper boundary condition. So we have this fixed. This should remain, no problem, but we have this fixed. I don't want to have this fixed. Yes. Let's have it, no problem. Let's duplicate again. Fixed shaft, which is not correct. So remember about the pressure and the fixed support on the tarmac. Yes, so pressure, fixed support on the tarmac and displacement. Let's see what we'll have. All right. Do I still have that frictional contact? Yes, I have it here. Yeah, this is a problematic contact. This is a problematic. Let me press adjust a touch. Let me change adjust a touch. It can only help. And apply a pinball radius. Yes, let's apply a pinball radius. Auto detection. All right. Save. And the mesh here, let's make it a little finer. Ooh, too good to be true. All right. So these nodes can find these nodes. Should I go gradually? Let's leave it like this. Come on. Let's look at the time increment. Yeah. Contact problems. Any question from the audience? No question. All right. What do we have here? Again, rigid tires. Yeah, looks nice, nevertheless. You know what? I might be trying to do this in explicit dynamics. Because there I don't have convergence issues. All right. Let's force convergence. You know, desperate times call for desperate measures. Stabilization, 0.01. Yes. 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 Let's see now. I think I can overcome all these if I have bonded contact here. But I kind of wanted to see it roll a little. Let's see if it rolls a little. My computer fan stopped, so I think the FEA stopped. So performing FEA live is not for the faint-hearted. It requires much experience and composure and cold blood to be able to come up with various workarounds or tricks in order to make the FEA solve and obtain results live. It's yeah, it takes much experience. What you are left with, some lessons, some hints, and a scenario that you can further optimize. You can ask for our files. For these files, you will receive the geometry, these ANSYS files in exchange for a few coffees, to pay for our effort. Come on, go. Go where you are supposed to go. So slow. Let's firstly change. It's promising. Let's firstly change this to 0.1, and if it doesn't work, I will make this contact bonded. Of course, that it would work easier if I make a finer mesh, at least in some contacts here. But this would increase the solving time, and I don't want to extend the solving time. We're close to the end of the live stream. This is all. This is I'm simulating landing gear for the F-16. If you didn't see in the naming of the parts in the geometry. Oh, so nice. So nice. What have we here? Mm-hmm. No measurement unit. All right. Yeah, it looks so nice. And the front is there. It's on the right of the front. Come on, converge. Of course. Such high precision. People's lives are at stake, so this is why we need such high precisions in the manufacturing process. Yes. This is the tire. Yeah. It looks like a suspension to me. Like an air suspension. But it might be the tire after all. Yes, it's the tire. Oh my god, the threading. Uh-huh. For fun, let's see the price of a tire. I think it's for small airplanes. 8 ply. Oh my god, so much work. Nitrogen, yes. Yeah, so much work. It looks like it's doing something. Come on, show results. Please show results. Oh. Oh. It looks nice. And the tire is inflated. Yeah, it looks nice. I will let it solve a little more. Then I will finish solving offline, and I will publish the solved scenario in the next days. But it's promising. It's touching here. Yeah, it's promising. Let's let it solve a little more. Then we can stop the live stream, and we can see the results on my YouTube channel in the next days or next week. Yes. Yeah, it's nice. Yeah, nice. add-ons. Even after so many years, they didn't improve the graphical user interface. I know this is an old, but the add-ons, I think it looks similar also today. And they're wondering why so few people are using such software. So it's clear to me and to everyone that the FEA is working. So we can stop here. And I will publish the results in the next days. So look, it's very nice. And we have also, a flat face here. It will become flatter and flatter the more pressure we have, this one. Do we have a section here? Let's see. Yeah. Can I move this? Yes. So you can see that it's flat here. Total deformation. Can I see the stress in the rubber? Let's see. Yeah, it's flat. Look here, this is a properly inflated tire. And the stress, how does the stress look like? Here, yes. This is how it's supposed to look like. At least on the outside, yes. Look here, yeah, it's flat. We have higher value inside because the pressure is applied on the inside. So it's propagating from the inside to outside. So yeah, so it looks very nice. So I'll finish solving offline and wait for results in the next days, which I'll publish on explicit.com. They will be available for download, for purchase, no problem. So thank you for your patience. Let's see if we have any question. We don't have any question. Yes, have a nice day and all the best. Bye-bye.